visible spectrophotometric sensors have become valuable tools for monitoring nitrate concentration. These sensors, initially used in wastewater treatment, are now applied in groundwater and surface water monitoring due to their ability to provide real-time, reagent-free measurements with lower maintenance needs compared to other methods to study or to determine the concentration of nitrate nitrogen in groundwater using UV visible spectroscopy. Next, we evaluate the effectiveness, accuracy, and limitation of UV visible spectroscopy for nitrate analysis compared to alternative methods. Next, we provide insights into how spectroscopic data contributes to the qualitative and quantitative understanding of nitrate pollution in groundwater. And lastly, we compare the performance of a double wavelength spectrophotometer and also a multiple wavelength spectrophotometer for determining nitrate nitrogen concentration in emergent groundwater at the spring discharge sites.
The method used in this study focused on analyzing nitrate and O3N absorption by examining light adsorbent below 250 nanometer and applying the Lambert-Beers law to relate adsorbent to concentration. Interferences from turbidity, organic particles, and O2N and humic acids were accounted for using multivariate data analysis methods. The study was conducted at two locations. First is Spring A and agricultural catchment in Ireland, and the second one is Spring B and urban catchment in Jordan. DWS and MWS were employed with different path lengths for measurement and 2-point or 4-point calibration. Observed concentrations range from 10 to 14 mgl -1 NOx(N) in Spring A and 11 to 15 mgl -1 NO3(N) in Spring B. Laboratory validation was carried out using Aquacom 600A and Dynex ICS 2100.
Differences between both sensors despite the measurement method for the multiple wavelength spectrophotometer is cleaning device. The multiple wavelength spectrophotometer offers a cleaning device as an optional hardware update, while the double wavelength spectrophotometer includes a built-in wiper for cleaning, which is crucial for use in natural water. Meanwhile, for cost, the double wavelength spectrophotometer is less expensive compared to the multiple wavelength spectrophotometer. Lastly, measurement data. Both sensors provide raw absorbance data, but the methods differ. Double wavelength spectrophotometer use two wavelengths, while multiple wavelength spectrophotometers uses the full absorbance spectrum.
This section focuses on the calibration and accuracy of the DWS and MWS systems for measuring NO2N in water. The DWS sensor demonstrates good accuracy for spring water A with a standard 2-point calibration, achieving an RMSE of 0.42. In contrast, the MWS system achieved even better accuracy RMSE 0.36 when calibrated using local spring samples and a second-order polynomial model. However, the accuracy of the MWS system declined with off-site calibration and linear on-site calibration, resulting in higher RMSE values of 2.11 and 0.82 respectively. These results highlight the importance of calibration methods tailored to specific water matrices to ensure optimal measurement precision. The findings underscore the value of localized and advanced calibration techniques for improving analytical reliability in water quality assessments. This study explores the influence of additional substance on NO2N absorbent in water samples. Elevated absorbent below 250 nanometer confirms the presence of NO2N, but interference from use of organic matter and other ions impacts accuracy. Isobastic points reveal variations in metric composition, with Spring River pond water showing higher absorbent than spring waters A and B, despite lower NO2N levels, highlighting interference effects. Derivative methods effectively reduce signal interference, enhancing the reliability of NO2N concentration differentiation. However, interference beyond 250 nanometer limits method selectivity, particularly in samples with high organic content. This comparison between DWS and MWS systems shows that while DWS use absorbent differences for partial interference robustness, MWS employs derivative techniques for greater accuracy by addressing signal overlap directly. This highlights the critical role of advanced analytical methods in improving water quality assessments.
While UV spectroscopy offers numerous advantages for nitrates analysis, it is not without limitations. However, targeted recommendations for improvements can significantly enhance the method's performance and its applicability. One major challenge is matrix interferences. It is caused by organic matter, turbidity, or suspended solids which can obscure the nitrate signals in the UV regions. To address this, advanced sample preparation techniques such as solid phase extractions or ultrafiltrations can be employed. These methods help to remove interfering substances, ensuring more accurate and reliable measurements. Next, UV visible spectroscopy also struggles to differentiate closely related species such as nitrates and nitrites, especially in complex water samples. To solve this, the solution is to choose combined UV visible spectroscopy with a complementary techniques such as ion chromatography for enhanced separations and identifications. Additionally, using a spectrometers with higher spectral resolutions or employing advanced algorithms for spectral deconversions can further improve these differentiations. Next is environmental factors such as temperatures, pH, or turbidity can influence measurements, which leading to variability in results. So, to solve this problem, by developing temperature compensating models or algorithms can help account for these variations. Furthermore, using multi-wavelength approaches can reduce the impact of environmental factors and ensuring consistent results across these diverse conditions. Furthermore, current detection limits may not always be sufficient for ultra-trace analysis of nitrates in pristine environments. So, by optimizing the optical path lengths or employing highly sensitive photodetectors, it can enhance signal intensity and lower detection thresholds. Additionally, coupling UV visible spectroscopy with pre-concentration methods such as evaporations or ion exchange receipts, this can improve detections of the ultra-nitrate levels. And lastly, limitations is frequent calibration is needed, particularly for fields applications. This is to maintain accuracy, which can be time consuming. So, to solve this, we employ an automated calibration system with built-in standard solutions to reduce manual interventions. Moreover, incorporating machine learning models can dynamically update calibration curve based on the real-time measurements. Can improve the efficiency and adaptabilities in the field. Why is it important to analyze nitrates, nitrogens in groundwater? First, high concentrations of nitrates in drinking water consumed will cause a condition called methemoglobinemia, also known as blue baby syndromes, which affects oxygen transport in infants. Moreover, chronic exposure to nitrate is linked to the formation of carcinogenic compounds, increasing the risk of certain cancers and other diseases. Second, excess nitrates in groundwater also has severe environmental consequences. It contributes to eutrophications, where the overabundance of nutrients trigger harmful algae blooms and oxygen depletions in aquatic ecosystems. This degrades water quality and biodiversity. Nitrates contaminations primarily stem from agricultural runoff, urban wastewater, and industrial discharges, making it a pressing issue globally. To address these challenges, regulatory framework plays a crucial role. International initiatives like the EU Water Framework Directive require a strict monitoring to ensure water quality remains within the safe limits. For example, the WHO and many countries have set the standards of 10 mg per liter nitrogens in drinking water to protect public health. Monitoring nitrate levels also aids in effective aquifer management. It helps us to understand nitrate mobilizations and dilution dynamics, especially in complex systems like karst aquifers. This knowledge is essential for sustainable water resource management, particularly in regions experiencing rapid urbanizations and agricultural intensification. Why UV visible spectroscopy was chosen for this analysis? First, UV visible spectroscopy offers an exceptional sensitivities and precision. It can detect nitrate levels concentration as low as 0.02 mg per liter, which makes it suitable for monitoring even trace levels of nitrates. Compared to non-selective electrodes or titrometric methods, UV visible spectroscopy relies on absorbent spectra, making it more accurate and reliable for nitrates detections. Next, this technique is cost-effective. The instruments are affordable and operational costs are considered low. Compared to more advanced analytical techniques like HPLC or GCMS, UV visible spectroscopy provides significant cost savings while still delivering reliable results. Another reason for choosing this method is its simplicity. UV visible spectroscopy is user-friendly, requiring minimal sample preparations. It is suitable for both laboratory settings and fieldworks, and importantly, it doesn't require highly specialized reagents or expertise, thus making it accessible for routine monitoring. Another key advantages of using UV visible spectroscopy is speed. It enables rapid, real-time measurements of nitrates, which is especially important for dynamic environmental systems. It is significantly faster than traditional wet chemical methods such as cadmium reductions or ion chromatography, ensuring a quick decision-making when needed. This method excels in accuracy and precision, particularly when using instruments like the multi-wavelength spectrometer, which has a broad spectral range from 200 to 750 nanometer. Calibration with site-specific water samples further enhances the accuracy of nitrates measurements, making it a robust tool for a complex water matrices. Finally, UV visible spectroscopy offers a high selectivity. Instruments like the MWS can differentiate between the nitrates and nitrites, while tools like DWS provides reading for total oxidized nitrogen. This feature allows for more comprehensive and specific nitrates analysis. In conclusion, this study highlights the critical importance of analyzing nitrates in groundwater to address heart rates, manage aquifers, comply with regulations, and combat environmental challenges like eutrophication. UV visible spectroscopy proved to be a reliable, cost-effective, and user-friendly method for nitrates analysis. While challenges such as organic interference and calibration needs remain, advancements like multi-wavelength approaches, enhanced algorithms, and automatic calibration systems offer a promising solutions. By refining and optimizing these methods, we can ensure precise and efficient monitoring, contributing to global efforts to protect water quality, public health, and environmental sustainability.